a pretty gruesome problem ahead. Um, I guess let's buckle up and dive in then. So our statement reads, for part A, suppose the wire in example 10.2 carries a linearly increasing current, I of t is equal to kt, for t greater than 0. Find the electric and magnetic fields generated. B, do the same for the case of a sudden burst of current, I of t is equal to q, not Dirac delta of t. Okay, this is different than what we've seen because we saw the Dirac delta used in the used with positional coordinates, not temporal coordinates. So this is a fun change up. As we saw last time, the generalized potentials for the non-static sources and the retarded time are given as such. So we find those, then we can find out what we need to do. So this is just going to be messy, so let's just be very, very careful. As in example 10.2, for t less than s over c, a is 0, and for t greater than s over c, we only have the line segment that actually contains any information that was getting to the field for z, magnitude z, less than or equal to the square root of c squared, or ct squared minus s squared. Again, that's just a distance formula, which if we draw it out, I think we did draw it out. Yeah, we have some point with the wire carrying the charge through dz. I'll go ahead and plug that in. Script R, again, we have from the source to the field point, z is the axis length, and s is the distance from the point to the wire. I can't speak. But yeah, once we see that we have to be within that certain symmetrical space, otherwise the news simply won't get there. Okay? So we have to keep in mind that t has to be within the bounds of the retarded time. Again, kind of messy, a new perspective to have to work with, but with that sets up our bounds on where we need to have our integrals from. So because the segment has to be less than or equal to magnitude z, we can have plus or minus with that square root there. Okay, now again, c is in meters per second, time is in seconds, so our units here are meters, and so meter squared minus meter squared and the square root give us meters back. So we're perfectly acceptable to use the temporal coordinate t with a rate of change c in the dz integral. Okay, again, very, very different than what we had ever thought we would deal with. That being said, we have a linearly increasing, what did it state? Linearly increasing current, so current equals kt. So here we have to evaluate the kt at the retarded time, hence k of t minus script r over c. Okay, now we're able to kind of push our way through this thing. K is a constant, so we bring it out front. We notice that we have a symmetrical setup here, so instead of going from negative square root to positive square root, we're just going to go from 0 to positive and put a 2 out front. And that 2 will condense down with the 4 from the 4 pi in the denominator. Okay, that being said, our script R that we saw from the diagram has to go as a triangle, hence we get the s squared plus z squared in the square root. No big deal, the Pythagorean theorem, let it be what it is. Now what we can do is split up the integrals for the numerator. One integral for the t and one integral for the square root of s squared plus z squared over c. So when we do that, we simplify down, split them up, no big deal. We see how nice that second integral cancels out with the script r over script r, and we're just left with the 1 over c times the upper bound. Now, unfortunately, the time component of the dz comes out front, but then we're left with a reciprocal, so we're going to have a natural log. And you see that when we plug in 0 for something, we get 0 for the z, we get the s's there back. So we just got to be really careful Again, I would suggest using a integral calculator if you're not comfortable with them, and to save yourself a little bit of time. But nonetheless, pretty quick there. Once you have the actual setup that you need based on evaluating everything within the realm of the retarded time. Okay, so we know here that since V is equal to 0, the scalar potential that is, that our electric field is just the time derivative, negative time derivative of this retarded potential A. So take the time derivative. It looks like we got a product rule here. It's going to get messy, as you see. Again, I would, just, it's gross no matter how you cut it. If you need to use Symbolab, Mathematica, something to help you simplify this, it gets gruesome really, really fast. Even with the simplest stuff like the second part of that bracket. But nonetheless, try to hang in there, clean it up as best you can. And you see that after a lot of cleanup, we get a cancellation here. Admittedly, I used a calculator myself because this was going to take too long otherwise. But after the cleanup, we get negative 𝘰�0𝘵 over 2 pi times ln of ct plus the square root of c times t squared minus s squared over s in the z-hat direction. Again, be very careful since we know for the B field we have to take the curl, but since since A is only a component in the z direction, we only need one derivative there for the curl, which is namely negative d by ds of az. Alright, so go ahead and do that. We see that after we apply that, we're left in the phi-hat direction. So again, be very careful with all these derivatives. They're messy. The derivatives are not the hard part. I think we've done enough of that throughout our calculus careers, but the simplifying is definitely a mess. And then, of course, we use this multiply by 1 trick. So I used color-coded that in red so we can simplify down, find a common denominator, and make our life as easy as we can for this. We see that simplifying part doesn't hurt too bad. And we see that we're left with B as a function of S and T, which is equal to 𝜇0K over 2 pi SC square root of CT squared minus S squared in the phi-hat direction. All right, that was a headache all in itself, but we still have a couple more parts to go. In part B, we note that for this, script R is equal to S squared plus Z squared, so it is even in Z, okay? Remember, part B was looking at for a sudden burst of current, okay? That being said, the Dirac delta again has to be evaluated at the retarded time. Since the news has to travel at the speed of light, the retarded time tells us the field that we're measuring came from the source at some other point. All right, so everything with respect to the retarded time. That being said, again, symmetrical, so we use the 2 again to reduce everything down, doubling it. Q0 comes up front as a constant. And then, let Z for here, since we're looking at script R and so forth, if we let Z equal square root of script R squared minus S squared, dz is equal to this monstrosity, which I'll let you read off, simplify it down. And we see that if we change the limits for Z equals 0, script R equal S, and Z equal infinity, script R equal infinity, now we can evaluate everything we need to with respect to what's inside the Dirac delta. That's the whole purpose of the change of variables, is so we can evaluate with respect to the Dirac delta argument. Notice that 1 over script R cancels with the script R from the substitution. And now you see for one of the properties that we found back in chapter 1, we can get rid of that C in the denominator of that script R. And if we multiply it through, we have to change the order rather we're factoring, yeah, we have to change the order and push a multiple out. So that's how we get the C, Dirac delta, script R minus CT. Now this is times dr script R squared minus S squared. And with this shifted Dirac delta, we know in our next step, we're just going to have to evaluate the integral at the location of script R equals CT. And sure enough, that's what we see here. Again, 0 if CT is less than S, otherwise we don't have any news due to the retarded time restriction. And we see that a S of t is equal to mu naught Q naught times C due to the Dirac delta property over 2 pi. And now we have to evaluate the integrand at CT, script R equals CT. Excuse me. So that's how we end up with this vector potential here. So after that, now we just find the fields with the proper derivatives, and we get a pretty clean slate with those derivatives. Excuse me. Now we get a pretty clean slate. Time derivative is easy, and the spatial derivative is easy, all things considered with our first question, and now we're pretty good to go. Those Dirac deltas are very, very handy, but you have to remember their properties, and you have to remember that if you want to evaluate with them, you have to be in the same argument sake. And like this integral was with respect to dz, you have to put it in respect to script r. So a very useful problem, but a very messy learning curve with it, but still fun nonetheless.